Our next speaker is Nicholas Rubin from Google, and he's going to tell us about industrial applications of Hamiltonian simulation and beyond, the prospect of NISQ and fault-tolerant algorithms. So, welcome.
All right, thanks for having me here. It's kind of a rare, I work up here in San Francisco, even though most of the Google Quantum AI team is down in Santa Barbara and Los Angeles. I'm part of the algorithms team, and so sort of our goal is to figure out what to do with quantum computers and sort of convince Google executives that it's a good idea to continue to build one of these. And so I'm going to talk a little bit about that in the context of industrial applications. So where specifically in sort of chemistry and material simulation industry, they use Hamiltonian simulation and sort of what that accuracy bar is. And so I'm going to talk about a NISQ experiment that is really a collaboration between myself and then Bill Huggins and Tom O'Brien, looking at generalizations of purification techniques. And then also I'll talk about sort of some fault-tolerant algorithms. I know the topic of the conference is not that, but I do want to put that out there just to kind of set the bar for what industry applications sort of look like and what are the scale. Okay. So yeah, if you go and look at chemistry or material science and industry, you get problems of this scale. So I think probably everyone has heard of the FMOCO active space or active site of this enzyme that fixes nitrogen. It's this big challenge problem at least in quantum chemistry, and it's been used as this benchmark in quantum information to kind of benchmark algorithms. You can ask things about drug discovery. I mean, these are sort of the normal things that if you pick up, the newspaper and you see someone talking about quantum computing, they say this is what it's going to be used for. People talk about battery cathodes and some other catalysts. And I just wanted to kind of put out there that like quantum chemistry has been developing for the last 50 years, and we are quite good at simulating these systems. And so I sort of put whether they're solved or not here at the bottom. This one maybe should be semi-solved. But yeah, we can simulate and describe these systems very, very well. So I want to kind of touch on where quantum computing sits in front of these, in these contexts. Okay, so I've sort of been, I'm a quantum chemist by training. I entered the kind of quantum information field in 2016. And since then, I've been sort of keeping track of NISQ experiments. I mean, this is not an exhaustive list, but it's some of the bigger ones. And so starting from 2016, there's this 2-qubit experiment, there's the 4-qubit and 6-qubit experiment from IBM. And then fast forwarding, we have a 12-qubit VQE experiment, a 10-qubit VQE experiment that I'm going to be talking about, and some larger simulations that aren't actually in the VQE setting. But this is sort of to benchmark sort of where we are in the field in terms of NISQ experiments. And that these are all well within the regime of what chemists would really consider classically simulable. And I think this goes along exactly with the previous talks in terms of where we are. Okay, so I want to kind of rewind to 2019. I still think that this is the largest VQE experiment that was done. Sort of after the 2019 supremacy experiment, Sergio sort of asked what you should do with one of these devices. And of course, in my infinite wisdom, I said you should run mean field theory on this very expensive object. But it's actually really great because it's a primitive for a lot of the other circuits. In fact, these Givens rotation circuits have a lot of similarity to the Clifford-Loader circuits that were actually discussed earlier. And so there are a couple of really nice things about this. So for what we're doing in this experiment is starting in some basis in second quantization, and we're performing a quadratic Hamiltonian evolution, and that can be decomposed as follows into these kind of 2 local gates. These are all match gates for those of you who would like a complexity characterization of this circuit. This is all efficiently simulable. And so there are some nice things about this. We can verify the results. We get gradient estimation for effectively free. We measure the 1 RDM of this system. For free fermion circuits, they're completely characterized by their covariance matrix, hence called Gaussian circuits. The covariance matrix is effectively expectation values of the second moments associated with that. And then we can use purification. And so what I mean by purification here is that I can project my 1 particle density matrix or my covariance matrix to a matrix that has eigenvalues 1 or 0. And so that's a very powerful thing to do whenever you're projecting. And that completely characterizes the circuit that I have. And we can look at the power of kind of the standard error mitigation processes, starting from the sort of raw data up here. This is the energy error for a particular model. In fact, it's the hydrogen chain here. And we can see what happens when we just have the raw data. We can have post-selection, purification helps a lot, and then VQE does do something. And there's a fidelity witness for these particular circuits that we can actually back out a lower bound to the fidelity. And so this looks quite good, but we are really relying on the power of this purification, this projection to a idempotent density matrix. Okay, so we want to take a step towards more difficult simulations, right, to really kind of see what is possible in the NISQ setting. And so sort of my proposal for a sort of intermediate step, instead of doing the entire fermionic simulation problem, what we can do is sort of stop halfway. And so in chemistry, normally we kind of partition up our Hilbert space into sectors that correspond to excitations from some particular Fermi vacuum, right? So that in some cases, if you're in condensed matter, this might be the BCS state. If you're a quantum chemist, this is like a Slater determinant of the mean field state. But really, we break up Hilbert space and looking at the number of excitations out of that. And so this is sort of a characterization of that. And the number occupation space, these are the Slater determinants here. And if we force ourselves to work in a space where all electrons come paired, this is actually called the seniority zero space. And we can project our electronic Hamiltonian here, describing the electrons in any chemical system or condensed matter system, into a spin model here. And so what this sort of says is that for every kind of complicated looking two-body fermionic model, there is a spin model, a Heisenberg spin model, that sort of lives in a subspace of this. And so that's sort of the model that we're going to target simulating as this intermediate regime between mean field theory and an exact simulation. Okay, so there's a couple of really nice things about this classically. So I said before that we usually work in some particular Fermi vacuum. Classically, what we can do is solve the couple cluster equations. This is a many-body expansion of the wave function where we do a similarity transform of the Hamiltonian, and then we just use Wick's theorem to evaluate all of those matrix elements. The BCH expansion truncates at order 4 because our Hamiltonian only has two-body interactions, and this is a non-unitary transformation. Okay, so that's all actually very efficient. In fact, in this case, it's cubic scaling. So again, we have something that's close to our experiment that we could possibly verify. Our quantum ansatz is going to be a unitary form of that. And that's some fabric of gates that we've sort of seen before as a nice dense layer of gates in one dimension. And this is a composition of something that's a free fermion rotation. So this is a quadratic fermionic Hamiltonian followed by a swap operation. And so this lifts it from the family of match gates into something that's BQP complete, actually. So that's the kind of gate set that we're going to work with. So formally, this is not simulable efficiently, but it does have an analog that is efficiently simulable. Of course, if we get rid of the swap, then this whole thing, again, is free fermions. Okay, so what we wanted to do is actually test two versions of a error mitigation strategy that sort of generalized this idea of purification that we had in the Hartree-Fock experiment. And so the two ideas are actually quite closely related. One is called virtual distillation. The other is verified phase estimation or echo verification. And they sort of work in a similar way, but they look at face value quite different. And so starting with virtual distillation, we know that if we take a density matrix and raise it to some power, right, we're projecting, we converge to the highest eigenvector of that state exponentially quickly. I mean, this is the basis of Lanczos method, right? And we know that if we can measure our expectation values with respect to that and then renormalize by this trace value, then we can potentially get error mitigated expectation values, like, for example, the energy of our system. And so this is called virtual distillation because we're never actually explicitly building this matrix power here, or this density matrix power. What we're doing is sort of simulating it in effect. So this is a well-known trick in quantum information. You can use the swap operator here, cyclic permutations, on a tensor product of your density matrices to simulate this higher order row. So this has been used, I believe Jordan Kotler's, the first use of this actually maybe was getting cooler, so doing a virtual cooling of some thermal state, and that sort of inspired this work. But you get circuits like this where you run 2 copies, for example, if this n is 2, you run 2 copies of your experiment and you do this swap operation and then you measure. So in a similar fashion, where we've doubled our space complexity here, we can actually do something quite similar and unroll it in the time dimension. And so this is the kind of core of the verified phase estimation. In this case, we have something that looks quite like an echo verification circuit. We have our state preparation unitary, our observable, and we want to unprepare, and then we want to project back on our 0 state. And we know that at least up to this square, our expectation values of any of observables are the survival probability of this particular circuit. And so, with some approximations about what the noise is doing in these circuits, at least in the forward direction and the backwards direction, we can say that as you introduce noise, it's effectively a scalar on the fidelity of your circuit times this expectation value. So there's a couple things that we can do. In a similar fashion that we estimated this kind of purity denominator, we can estimate this fidelity by removing the observable, rescaling, and then of course we can get rid of the square by using a controlled operation. I mean, this is effectively what you're doing in a swap test. This is just a block encoding with 1 qubit, right? And so that's sort of the core of verified phase estimation. It's unrolling in time what we're doing in virtual distillation in sort of a morally similar fashion. Okay, so what happens in this experiment? We have that unitary pair couple cluster ansatz, and we had to do a couple of things, right? In the virtual distillation, we need to have 2 copies of this and then swap, and then in the echo verification, we need to run this forward and then backwards, but with a observable here in the middle. And so the circuit that we use is actually on a ring. That way it makes the measurements of an all-to-all connected Heisenberg model a little bit easier. And it sort of starts like this, where we assign some initial Fermi vacuum here. This is the half-filling state, for example. And then we run this fabric, as I showed in the previous slide, and then we do these swaps at the end for measurements. Again, since we're working with qubits now, because in the seniority 0 space, all electrons are coming paired up, and that forms a SU2 algebra that we can just map directly onto our Heisenberg model. So that's sort of how we get from fermions to qubits and why there's no like fermionic language in this particular circuit representation. And so sort of in the same way that the Givens rotation circuits are linear depth, we sort of do the densest possible first order Trotter approximation of that unitary where we have this Givens rotation fabric or Givens swap rotation fabric. These are not match gates, but fully universal. And so for the echo verification case, we needed to do that control to get rid of that square. And so what we do is actually a non-controlled version of this where we create a superposition in the initial state between a state where our unitary acts, or our generator of dynamics acts as an identity, and this initial Fermi vacuum. And so what that is just a GHZ state, right? And so we produce a GHZ state, we run our dynamics, we measure our observable, or we time evolve our observable because we're trying to get, we're doing sort of a phase estimation here, and then we run this back and we post-select on 0. Okay, so those are the 2 schemes, and that's sort of what's happening in this experiment. Okay, so the system that we sort of looked at was, there were 2 actually. The first one is this Richardson Gaudon model. It's a model of a superconductor. You can think of this is just the BCS Hamiltonian where this can be tuned, right? It's nothing sort of fancy. And if we look at the performance of the device, let's just look at this top left box here. The raw VQE here is sort of up here, and this is quite a large energy error. We can post-select, right? Effectively, we can post-select on 0 and for virtual distillation on number operator. And then applying the echo verification and the virtual distillation, these are quite accurate over the entire parameter regime. This is sort of a cute little model because we know that pair couple cluster diverges in this regime, so we would not be able to accurately simulate that in this regime, and we know that BCS is sort of wrong in the other regime here. And so it's kind of a nice little example where sort of your 2 first classical approximations are not going to get this right. Of course, this is a 10-site system. You can easily simulate this, and there's lots of other techniques that you could use to dial in the classical side. But in some sense, this is to demonstrate the two error mitigation strategies that are sort of this generalization of the purification. So here are the sort of energy errors that kind of similar to what we were showing in the first experiment. These are quite large, I think, when you kind of compare that to what is needed for chemical simulation. But maybe in this setting where you're looking more at an order parameter, and this is the superconducting gap order parameter, you don't need such tight accuracy considerations. And so this is sort of a similar story. If you pick your observables correctly, you don't need as tight an accuracy bound. And so this is quite nice. Echo verification and verified phase estimation perform kind of similarly. They provide an order of magnitude improvement over the kind of unmitigated VQE, and this is quite a robust protocol. At least the circuit is capturing the physics of the model. Namely, we're getting this entire regime here. Okay, and of course, as a chemist, I don't want to publish a paper without a molecule in it, really. And so this one is an example of a sort of kind of canonical reaction. In fact, it's the canonical example of Woodward Hoffman rules. Got the Nobel Prize in 1986, I believe. And here what we're doing is we're taking a cyclobutene, which is a square molecule, and what we're doing is we're pulling it apart into a diene. And so there's a particular pathway. In fact, in molecular orbital theory, quantum mechanics is explaining specifically how this is going to ring open. And so what we do is simulate that on the device with this in the seniority zero space to see if we can kind of accurately model that entire pathway. And so again, this is in seniority zero. The kind of smaller system is 6 qubits. The 10 qubit one is right on top of it. Of course, going to a larger Hamiltonian here in terms of the active space isn't kind of giving you a lot. But we are capturing dynamic correlation between, namely, the part of the Hamiltonian that you would get by a perturbative expansion of your wave function. That's effectively the gap between this red line, which is mean field, and these blue curves. And again, this story is sort of similar. At small scales, error mitigation works quite well. But if you want to scale this up to something reasonable and demand the accuracies of chemistry calculations, these are nowhere close. So these green points here are all of the 10 qubit echo verification data. So in terms of parallelity with this curve, that's pretty atrocious. And the error bars are very large because this is a very shot-hungry protocol. Effectively, as the fidelity goes down, you're post-selecting on 0. This becomes a more and more difficult thing to do with statistical certainty. The movement of these as a function of the reaction coordinate here sort of also tells us that the device was drifting quite a lot. Okay, so that sort of ends the story on NISQ. Didn't want to dwell too long on that just because it is, I guess the takeaway is that it's quite difficult, even with fairly sophisticated error mitigation that is doing a projective or a projection, namely something that's purifying your state. We can kind of design protocols that are doing that. It's still quite expensive to do chemistry simulations at a quantitative level. And so, mm-hmm. Mm-hmm.
What exactly would you need more qubits for here, and what changes that you have more qubits? So I'm assuming that you need more qubits if you want to do something interesting, but how does that, how precisely does that translate? Is it a bigger molecule, or is it just doing the same molecule but understanding it better? So where does the number of qubits come in, and how should I think of it intuitively?
Yeah, that's a good question. I sort of breezed over some of that. So, like normally when you simulate a molecule, the Hamiltonian is defined as some the differential operators is a partial differential equation that's continuous, right? And so the first thing we do is pick a basis to discretize, right? And so in some sense, that's setting the scale, the number of qubits of your system, right? And then there's a question of, given a mean field guess, right, the degree at which you need different Slater determinants to describe the full system. So for example, if you have a Hubbard model or a spin liquid or something like that, you might need a lot of determinants to describe this. But for a lot of molecular systems, even if they're very, very large, they can be treated very, very well with perturbation theory. And that's sort of what I meant on the first slide. Some of those catalysts, they look like big molecules. You can imagine like 10 qubits per atom on that slide, right? But some of those, of course, are solved because couple cluster and perturbative expansions work very, very well. So that's sort of the setting. It's hard to tell a priori. And so you can effectively generate a Hamiltonian that's just the interactions around your Fermi surface. And then that can that's, for example, what we're doing here. We just say, okay, there's some number of occupied orbitals in this small little molecule. Let me just pick 3 above and 3 below the Fermi surface. I'm going to use that to define my seniority 0. And you can do that with much more complicated systems. I'll describe one at the end. But it is an art to do that correctly, because there the basis set matters, so kind of the one particle rotation that you choose matters, like all that stuff kind of goes in, and that's sort of where the chemistry bit comes back into the problem of simulation. Yeah, it's quite hard to give like formal results on this. Okay, but in an effort to give formal results, I'm going to talk a little bit now about sort of progress towards simulating something of industry relevance with fault tolerance. So we saw on the NISQ side that it's quite difficult to reach something that is very accurate, that my colleagues in industry at chemical companies would say, okay, that's a useful calculation for me to run. But what about in fault tolerance? So Google has a timeline for building this device, and we'd like to know sort of how big it needs to be and what we're going to be able to solve sort of at the end of the decade when we build it. Okay, so there's been a lot of progress. This table is certainly not everything, but it is a kind of compendium of the progress that has been made, at least in phase estimation. So I think Lynn was here yesterday talking about ground state preparation, but this is sort of a different form. This is just saying, let's define my system and how expensive is it going to be to do phase estimation, not worrying so much about the state preparation bit. Okay, and so starting in 2005 with Alon, when he was, I believe, here at Berkeley, there's, of course, it's known that in second quantization, this is going to scale linearly in the system size n, and there's going to be some polynomial dependence on the number of gates, right? And that was unknown. But then if you fast forward over the years, we have some fairly terrible scaling down to now something that's actually linear in the basis size up to this new parameter lambda here, and still linear in the space complexity of my problem. And so given this sort of improvement, one of the activities of our group is to sort of characterize, well, what are the constant factors associated with these algorithms? And so this is a fairly tedious process, compiling for a computer that doesn't exist yet, but it can be fun just to see sort of how long these algorithms are going to take to run outside of a big O sort of reasoning. So it's time for an honest assessment of what's going on here. And so here are some of the systems from the first slide that I showed. We have our Fumoko catalyst. Many of you have seen this. And then in this PRX particularly, it was calculated given a particular Hamiltonian decomposition, it would take about 4 million physical qubits and 4 days of runtime for one eigenvalue estimation. Of course, to solve the Fumoko problem, we would need many. There's a question. This is, so we're compiling this down to the surface code, and we fix an error rate that is below threshold, but not too far. And then we make some assumptions about the number of T factories we have, the cycle time of the surface code. I'll talk a little bit about that, but in some sense, those are sort of details, and you sort of just figure out exactly how fast things are going to be produced. In our case, it's going to be specifically how fast Toffleys are produced. But again, so this is this P450 drug target. Effectively, this particular this enzyme where this active site lives metabolizes about 50% of the drugs that are on the market. So when you design a drug, you actually don't want it to bind too strongly to this, because then If it does, you metabolize it and it's no longer effective. Again, similar sort of scenario, you could probably guess from the relative size. And this, to your question, Ramesh, is sort of where we had to be very careful selecting an active space. For example, here's an iron right in the center of this, and here's this carbon sort of ring outside of it. You might sort of expect that the iron is really where all the action is happening, and you wouldn't need to treat all of these at a very high level of quantum mechanical theory. And so that's sort of what we do, though, to describe everything properly here. You do need a pretty big active space. And then the other one is materials. This is definitely more recent work from earlier this year. We took a real battery cathode material. These are with our colleagues at BASF. And we cost out exactly how long it's going to take to simulate with some new method development here. Okay, so sort of what does that look like? This is sort of the kind of the mechanics of what we do. First, how do we simulate something within error correction for quantum chemistry? Well, we can prepare some wave function with a reasonable overlap, namely it's not too small with respect to the ground state. We form some circuit that's a propagator of a function of our Hamiltonian. The kind of canonical example is this function is the identity function, right? Just gives you your Hamiltonian back. And that means then our unitary would be at some type of trotter, right? But there's other functions that we can choose. And then, of course, application of this unitary, we know if we do this in a controlled way, via phase kickback, this is kind of basic quantum information, you can induce a phase on this eigenstate expansion of your initial state, right? And then we know from phase estimation that with probability that is proportional to our initial overlap, and with error epsilon, we need 1 over epsilon or queries to the U that is that we're going to build. And so the goal then is to say exactly how expensive is that U to build. Okay, so the modern forms of this, of course, are qubitization. Our qubitization forms are really just looking at particular block encodings. In this case, what that means is that our function of our Hamiltonian is actually this weird function, the arc cosine of our Hamiltonian, divided by this parameter lambda. Since we're dividing our Hamiltonian by some parameter lambda, of course, that scales our phase estimation complexity here if we want the same accuracy. Okay, so there's a lot of theory about what this can be, and I can talk about that at length later, but I just wanted to kind of just very quickly put up, like, this is the protocol that we're using and costing out. Namely, we have an estimate for how many queries to this U that we need to call, and then we cost out specifically how expensive is it going to be to build that U. Okay, so what are the space-time considerations when we talk about costing out quantum algorithms? So we're going to build a device that sort of looks like this. It's about the size of a school bus. These are all the control electronics. The qubits live in here. It's a quasi 1D architecture. And to the question earlier about what we compile into, we make an assumption about the surface code, and we make an assumption that there's some particular physical qubit overhead for to implement a logical qubit, and that we need to sort of pay attention to two different types of gate sets, or one particular gate set, but two different types of operations. One would be Toffele's or T-gates. These are quite slow in comparison to the other set, which are Clifford's. And so there's really a huge constant factor slowdown. And so if you're from the classical world, you kind of treat your gates, so like AND and ORs, to be the same complexity, or AND and XORs, or NANDs and XORs, let's say, to be the same complexity. But in this case, one of those takes many orders of magnitude longer. And so kind of the classical version would be this NAND gate. This takes a kind of space-time volume of a transistor nanosecond, right? And then a quantum NAND gate, or a Toffele gate, of course, this is as a space-time volume. If you sort of write down the entire distillation sequence, about tens of qubit seconds. And so it's certainly, we really care about these constant factors, especially with compiling to the number of Toffele states that we need. And so that's going to be the target. Okay, so very quickly, I know not everyone is probably familiar with kind of fault-tolerant algorithms and block encodings, but I just wanted to put this up. To build that arc cosine, we use a linear combination of unitaries framework. And effectively, there's two primitives that we cost out. There's this select primitive, which is effectively is a for loop, right? Select is taking some register, index L, our state, and applying the UElf unitary. So we're representing our Hamiltonian as a linear combination of unitaries. There's some weight and there's a unitary, right? So that's just a for loop, and we know how to write down a for loop on a quantum computer. In fact, we put the for loop on a binary tree, and we iterate over that with a depth first search. So that's exactly how it works. And then prepare is building a particular superposition. We can do something kind of similar. And then you can find many lecture notes on the particulars of what LCUs are doing. But in some sense, you can view it as a block encoding. Namely, this unitary is putting the Hamiltonian up here in this upper left block, and we apply the Hamiltonian to our state, of course, selecting on the ancilla qubit being like 0, for example. There's just one additional ancilla qubit, assuming our Hamiltonian has norm less than spectral norm less than 1. Okay, so if that didn't make any sense, that's fine. I'll get back to the chemistry stuff now. Okay, so we have these two primitives that we're going to cost out to build that arc cosine function, right? And we have our Hamiltonian that looks something like this, right? This is now the full Hamiltonian, not projected to the seniority 0 space or anything like that. And our goal is to represent it as a linear combination of unitaries. And that statement is pretty general. You can pick any set of unitaries here that you have an efficient implementation for. And in fact, that's sort of where the chemistry part comes back in. There's different particular factorizations of this 4 tensor, which is the Coulomb operator, right? There's two that there's no factorization case. This is in some tensor network representation of that 4 tensor. We have a SVD or a Cholesky decomposition, depending on your flavor of language. And then we have 2 types of hypercontracted forms of this tensor network. All these have different costs in terms of implementations. And this goes back to on that first slide of the phase estimation section I was talking about here. There was all those different complexities. Those complexities sort of come from the types of tensor factorization that you do. And so those are repeated down here for you. If you'd like to know specifically like where some of these complexities come from, why is this one linear, for example? How does lambda scale with n, the system size? Come talk to me later. But the nice thing is that with some of the more sophisticated hypercontracted factorizations, we can get sub-mean field scaling for performing a phase estimation on some of these systems. And so that's pretty cool. We can go to very large system sizes. Okay, so I sort of mentioned in the first slide, some of these are solved and some of these are not. But again, the goal was to sort of characterize if we had a large quantum computer, would we be able to solve some of these interesting problems? And so in that case, we need to set up a competition between classical and the quantum case. So this is quite difficult. It requires assumptions about compiling into the surface code. But we have a pretty good idea of what is possible from an engineering perspective. And we also know what's possible from a classical perspective. In this case, we're picking an active space. This active space is defined by picking this center iron and then sort of expanding the view of the number of orbitals, namely the number of qubits that were involved in this particular Hamiltonian. You'd expect if you kind of go out, the action is sort of here at the center and the orbitals become less important as you expand. And we can compare exact diagonalization, this is full CI here, DMRG with various bond dimensions to our estimates of the quantum runtime using the best methods that we have. And so this is pretty cool because we do get to see a crossover, at least an estimated crossover. Again, this is compiling to a device that isn't built yet. And so these are, of course, estimates. But we do our best to have these as upper bounds. So it's very likely that this is a little bit higher than we need. But there's new tools that we're developing, for example, software frameworks that let us express these algorithms that we can see exactly how bad our upper bounds really are. And so we guess that around 80 qubits, that's like right around here in terms of orbitals, that we'd see some type of crossover in terms of simulation time. And so this is pretty reasonable in terms of actual wall time. Of course, DMRG is close to embarrassingly parallel. And so you can sort of bring this down. What we did is make a comparison here as fair as possible, namely setting the number of CPU threads to the number of Toffoli factories or T factories that you have. Of course, you can scale down this complexity by adding more T factories, and you can scale down this by adding more CPUs. And so there's a little bit of an art to convincing people that this is a reasonable thing to do, but this also just gives sort of a general idea of what the first class of quantum computers that can do these calculations are going to look like in terms of the types of simulations they can do. Okay, so I'm going to wrap up with this part here soon. I just wanted to point out that we can do this on materials. I showed this earlier. Really the kind of cool thing about this work is that we took an actual question in industry. They want to simulate these lithium nickel oxide systems. The ground state of these systems is actually, there's a chemical question, namely, this should Jahn-Teller distort based on band structure theory. But from X-ray, it does not look like it does. And so this is a great example of something where an electronic structure calculation can at least help experimentalists interpret why that is happening. And so naturally, as compilers, we wanted to know exactly how long that was going to take. In order to do this, we had to introduce quite a bit new theory. We had to symmetry adapt all of the block encoding oracles that select and prepare to include abelian symmetries. Effectively, this is k-point sampling on a quantum computer. Again, we get here in this case, we get a quadratic improvement to unsymmetry adapted, but the costs for a system like this are quite high. And so sort of the conclusion is a little bit negative in this case. If you want to simulate at extremely high accuracy these particular models, it's going to be quite expensive without some new innovations in fault-tolerant algorithms. And so I think it's important to cost these out because we can actually stop just kind of leaning into the hype saying, of course, a quantum computer will help with this type of calculation. In this case, it does not. Okay, and so I'll end there, I think, with plenty of time. So I guess the takeaways that I hope everyone got from this, there's sort of two parts. That if we just look at VQE and variational algorithms of that flavor, it's very, very difficult to get to the accuracies where chemists would really pay attention. Everything that we showed there has a lot of error. We weren't able to produce the correct curves, though for some different types of problems like order parameters and superconducting models, this definitely requires slightly less precision, and so we can sort of get the right answers there. But even with fairly sophisticated error mitigation, where we're doing these purifications, effectively purifying the entire density matrix because we're taking powers of the density, it's quite challenging to get good expectation values. And then, of course, in the fault-tolerant setting, there is actually a lot of hope. If you take some of these algorithms and cost out specifically how expensive they are, there is a regime that these will be pretty useful calculations for a lot of practitioners in quantum chemistry and material science. And so I think there is certainly hope, and it is exciting as we kind of push forward in that area as well. So thanks for listening.
Hello, great talk. So following on Umesh's question now, if I understood what you said at the end there, you get a crossover at like 80 logical qubits. So then the question I have is, if I were in industry designing batteries, how many logical qubits would I actually need to be useful? Is 80 above or below that number? I mean, I still haven't quite gotten that from your answers earlier. I mean, how many do they actually need to be useful?
So I think this particular model is a bit special. We do see a sort of brute force, like if you were to try to simulate this active space at around 80 qubits, right? This model, a model of this particular molecule, because again, we're projecting down the size of that Hamiltonian to just an active set of orbitals. Around 40 orbital description is pretty challenging to do just from a sort of DMRG perspective. There is enough correlation. But I will say that as you increase the size of the active space, namely going from like 5 to 40, and you look at the electrons that are involved, it's the same 3 electrons. And there's a very chemical reason for this. there's an experiment that says that this compound 1 should be in a doublet state. And there's only so many ways that you can spin couple things that are spin half to form a doublet. And there's only so many electrons in this case that you can borrow from. And so the answer is going to be 1 electron, 3 electrons, 5 electrons, 7 electrons, odd numbers all the way up. And so since there's only the iron participating, and this is sort of the chemistry intuition coming in, it's very unlikely that there's more than 3 to 5. In fact, I personally believe there's 3. The reason that this is actually difficult is the particulars of the energetics of this reaction, namely this entire pathway, are very much dictated by what's called dynamic correlation, the things that you would treat at perturbation theory. And actually doing that is actually much more expensive than these DMRG calculations. And the energy levels of the different spin states move around quite a lot. And so part of the reason you have to grow to a large size here is actually to balance the contribution between those two energies to your answer, namely what's the ordering of the spin states. In the materials section, these unit cells have hundreds of electrons. And so I didn't explicitly put there, you can see sort of down here, even to describe the system, this is thousands of orbitals. And that's partially because anytime you're simulating a material, you have to, it's automatically harder because you're trying to converge it to the thermodynamic limit. And so the number of qubits required in these cases is fairly astronomical. And that's partially because of the methods that we use, but also just because these are huge Hamiltonians. The only level of theory that we could do here is effectively auxiliary field Monte Carlo and perturbation theory. It's extremely difficult. Of course, even describing the Hamiltonians, the 2 electron integrals there are gigabytes. And so you have to get all of that information into your circuit. And so that's where all of the compression techniques really start to matter. And so I don't have like a strict answer for how many qubits you would need in this case, just because it's extremely difficult to say. More than 80? Certainly more than 80 if you want to do this ab initio. If you want to build a model Hamiltonian, then it could be much smaller. That's why we must turn to embedding theories in some way. So.